Warning: no attempt of any of these demonstrations or experiments should be made without an adult or a specialist present. Any injury or accidents can not be directly blamed on any affiliation of Mathbusters, Mathbusters themselves, or Clark Sang Productions. Basically, do not try this at home. On this episode of Mathbusters, Maime and Ladam explain stress. From bridges to elastics, you'll see if a relationship between the two is really such a stretch. Using derivatives, can you find the maximum and minimum stress of an object? Let's get calculating with the Mathbusters. The square cube law. Stress is the measure of force upon an area, measured in newtons per meter squared. This measure causes the coinciding change of a shape upon the object from the external force, strain. Strain being the deformation of an object from its unaltered size measured by the change in length over its original one. The square cube law is a relationship between volume and surface area. As the length, width, and height increases for a cube, for example, its volume increases exponentially. Think of a 1 by 1 by 1 cube versus a 2 by 2 by 2 cube. The surface area increased only by 1 unit, but its volume increased from 1 to 8.
So how does stress and deformation tie into what we're doing today?
Well, there are three different real-life applications we can apply to it. For example, all these bridges, they have different types of stress and strain on the cinder blocks or the material that they're using. For slingshots, there's the elastic aspect of it, and there is something to do with biology. I don't remember which one that is.
Well, bones are a thing. We depend on our bones to support the day-to-day strain that we inflict upon them just by walking around. This uses the same idea as force being applied to an area.
That's true, but there's a misconception that applies to this a lot, that if a material can bend, it's not strong enough. So let's see about that. Alright, now for material.
Miniature wooden constructive beams. Sticky bonding strip. Foam conular receptacle. Constructive wooden writing utensil.
Safety first. Here you go. Here you go. Let's do this.
In order to demonstrate the idea of stress on a common real-life example, a bridge, Ladam and Maime are constructing some bridges out of different materials. Hopefully they'll stand up to their expectation. Man, look at them hard at work.
So these are the bridges we just built. This popsicle stick bridge and this styrofoam bridge. So even though you don't think so, this popsicle stick bridge is more elastic than the styrofoam bridge. Elasticity is the ability for an object to return to its original shape. So when you try to bend a popsicle stick, it easily goes back to its original structure, unlike a styrofoam bridge where once you bend it, it can't return. So therefore, the popsicle stick bridge will take more stress from weights like cars and stuff over the styrofoam bridge because it can take the strain. So, bridges. From a previous experiment, we found out that the strain inflicted on the bridge was 4 meters. So, at this point, we found out that the object reaches its yield strength. Yield strength being the maximum stress a material can withstand before it can no longer return to its original size. So, the relationship between the stress and strain of our popsicle stick bridge was represented by this. So, using this equation, we will find a derivative at 4. So, having used this calculation, we found that the yield strength was 0.63 newtons. Another application of stress and strain are in things like strings and elastics. So, an unstretched elastic shows the minimum amount of strain that it possesses, and a stretched elastic shows the maximum strain. At some point, the maximum strain exceeds what the elastic can take, and the elastic breaks. But in between that minimum and that maximum is the optimal strain that elastic can have that will give it its most optimal force. For example, a slingshot.
Alright, I'm going to draw a picture to help us understand our slingshot demonstration. Okay, so this is the equation we found to describe the relationship between stress and strain for the rubber band on the slingshot. So now we're going to derive our equation and set the derivative equal to 0. So when we set the derivative equal to 0, we found that there's no solution. So after that, we decided to check the endpoints. When we did so, we found that the maximum stress that this rubber band can withstand without snapping is 36.51 newtons.
So turning to biology, our last concept to illustrate stress and strain are bones. Different animals have differing types of stress affecting their bones. For example, humans versus dogs. Humans are taller and generally more heavy, so their bones experience different stress versus dogs, who are shorter and generally weigh less than humans. So, with all the calculations we did about yield strength or about, just the maximum stress that an object can take is really useful for engineers, civil engineers to be specific, or anyone that has to deal with what material to use with what, depending on if you're building a building or if you're building a skyscraper, right?
For sure. Calculating optimization and the instantaneous rate of change is used a lot in slingshots, bungee cords, anything like that.
Suspension bridges.
It's very crucial to know the exact amount of pressure that can be applied to a certain string before it breaks.
Yeah, because if you don't want to build it, you don't want a building to fall on itself because it can't support its own weight.
Obviously.
So you can even apply that to like I said, suspension cords for a bridge and stuff like the Golden Gate Bridge. See? And stuff like that. And even with bones, it's the same kind of criteria, right? You need the bone to be able to support the weight it's holding up. So, a giraffe doesn't have the same bones as a mouse. You know what I mean? It's just different weights and different things it has to do. So with the answer I got, which was 0.63 newtons per meter, that represents the yield stress, right? Which is after it exceeds that point, the material cannot return to its original length. So you can apply that to a lot of failure calculations because if
for bridges, for anything structural, really.
Yeah, absolutely. Because if it has a really low yield strength, then it can't take a lot.
Which is shown in our tiny number with a popsicle stick bridge, It wasn't the most structurally sound.
No, it didn't withstand that book. Completely demolished it. So clearly, we're not great engineers. We should not build bridges.
What does it say about that?
And stuff. And so with yours.
Yeah, for the slingshot, we found that the maximum force that can be applied to the slingshot without it breaking would be approximately 37 newtons. So you can pull on that slingshot with 37 newtons of force, and it should still be, intact. But,
That's true. Is that a lot of force? I'm trying to think.
Who knows? Go ask Mr.
That's in our next episode of Mathbusters. So that, kids, is Math Explained. That bridge on my sweater.
So go.
I have that bridge on my sweater. Math explained. It fell. No.
Show a little diagram to demonstrate what we are trying to demonstrate. What was the equation? Was it like 2 over 3? No, that's mine. No, yours was 4. Mine was, it was 4. Oh my god, okay.
Newtons and per square crap. Okay.
The strain.
Oh my gosh, is it showing up? Green on you.
Sure. Okay, would you stop?
It's an old man thing.
It's a